In several role-playing games like Dungeons & Dragons or Pathfinder, several players get together to play a game. In this game, loot tends to drop, and this loot has particular values. One quirk of these games is that loot sells for exactly half of what it's worth. If certain players are able to use more drops than other players, they're able to retain a lot more of the value of that item rather than just selling it for half value and using the cash to buy something else. In a previous video, I've gone over how wealth by level is derived from the game and what it means to each character. In this video, we're going to talk about a loot distribution method that attempts to keep each party member relatively equal. Now that we know how to calculate wealth by level for a particular player, let's look at this way of calculating. I call this method normalization because what we're going to do is create a ratio by which we can multiply the leftover cash in order to determine how much to hand to each player. As you can see in this example, player 1 has picked up a lot more items than players 2 or 3. And as levels go by, player 1 will simply use more items than 2 and 3. Now in an ideal world, each player would receive 1/3 of the cash that drops. It's very important that the ratio that gets multiplied by this cash sums to be 1, as you can see here. The sum of those three values is 1. They currently have a ratio of stuff that is equal to their own value divided by the total party value. So 3,000 divided by 5,700 is 5.3. Now I can't directly multiply these because player 1 has the most value and the highest ratio. So there's not too much benefit in simply multiplying this out. What we could do though is subtract the amount that he does have from the amount that we should hand out. But there's a problem. The sum of those values is 0 because we have 1 minus 1. So what could we do? Well, let's just play with the numbers a little bit and give everybody twice their intended value and then subtract off how much they own already. That gives us something more like this. 66 minus B9, C9, and D9. Now these values sum together to be 1. And player 3 is receiving the most coin, player 2 the middle amount of coin, and player 1 the smallest amount of coin. The trouble is, as these values go up, the difference between them grows smaller and smaller, so we'll be handing out closer and closer amounts of cash. But we want to hand out more in order to compensate and try to bring them up to level. So what could we do to the math to get that? As you can see, if we hand out 3,000 GP right now, player 3 is going to get 1,300, player 2 1,200, and player 1 400 to bring their new values to be this. And the question is this distributing value quickly enough? Here comes a concept called normalization. Normalization is the process of adjusting values so that they're more useful to you. What we want to do is create a multiplier where their sum across is equal to 1, like this percent difference here. Then we can multiply these values by the 3,000 GP we need to hand out. So can we use a common method of normalization, where we take the value minus the minimum value, divide by the max minus the minimum value? Well, not so much. This gives us bad ratios. That is, ratios bigger than 1. So we've got to adjust our strategy a little bit. But what if we just subtract off the minimum value. Let me show you what that looks like on our graph. We've taken the smallest number and we have completely removed it, bringing this 0 line up to the lowest line here. Now we're going to take an average of each and hand out cash accordingly. So player 3 is going to get the most cash, player 2 will get a little bit less cash, and player 1 will get significantly less cash. As we see here, once we take out the minimum value, the percent of value we have is 86, 14, and 0. So then, when we look at the percent difference, we have negative 19 because our 66% minus 86 gives 19, 52, and 67. So when we distribute our 3000 GP, it looks more like this. This is better, but it's still a little bit off. We've got a negative value here, which means player 1, if he's got 571 coin, is going to have to give that up. Well, that's suboptimal. What if player 1 doesn't have 571 coin to give up? Then he can't do this. So we need to buffer this a little bit. One way we can do that is by inserting a ratio. So we're going to take our minimum value and make it an almost minimum value. Right now I've chosen 0.9. So the value that we're going to subtract off is the minimum of the 3 players times 90%. It's 90% of the minimum value. We're going to subtract that off the top, and 3 times the almost minimum value off the total party value. So you can see here, and the sum equals 1. This got us a lot closer to 0 than that negative 19. But we're still handing out a bit of coin. One way to cover that is to create another ratio of reserved cash. In other words, the 3000 coin becomes 90% of 3000, and we simply hand out a third of that 10% to everybody. Phew, super complicated, right? Here's what it looks like in practice. So each of these green squares has my full equation in it. Looks something about like that. What that's doing is it's taking the amount of coin dropped for the previous level, multiplying it by this force distribution ratio, that is the gold I've set aside to hand out to players at the end, and multiplying it by this forced scaling ratio, the amount of the minimum that we're going to count. Currently, the coin that's going to drop is just going to be enough to bring the entire party up to average wealth by level. And it's subtracting off the loot that each player is keeping, just so that we can throw some values at it and see what it does to our graph here at the bottom. As you can see, our players start with vast differences. Player 2 has 10,000 GP more than player 1. But we resolve this in 2 levels. From level 7 to level 9, it's already fixed. And it stays fixed all the way up through level 20. As you can see, player 1 gets a lot of coin right now. Player 2 not so much. Player 3 gets quite a bit. And player 4 gets a middling amount. And these about equalize here. Now we're going to hand out some loot. See if we can make it all still match. So player 2 gets 1,000 GP worth of drops. Player 3 gets 4,000 GP worth of drops. And as long as we still have some cash to hand out, it can still converge. If one player takes all of the value and drops one level, everybody else flatlines, and that player gains a significant boost. And that's the point at which negative numbers hit. You may be curious why these are 0 and then it goes to negative numbers. That's because there's no cash to hand out at this level, and so it's using this cash, the 20,000 GP, for the next level to try and equalize. It uses liquid cash, that is the proceeds from sales, to balance it out. We're trying not to take money from players, but rather fix it in post by handing out more money to less equipped players. Let's just have player 4 get 4,000 in drops right now. We'll just hand out 5,000, how about 6,000, maybe an 8,000 here. And as you can see, our numbers are still fairly converging, even though player 1, being the poorest, has gotten no drops. He must be a monk or something like that. Alternately, even though he's the lowest on drops, he could start picking up all of the drops. So what if he picks up $1,000, 2,000, 3,000, 4,000, 5,000, 7,000, 22,000. How far can I push it? 40,000? Oh, there, that busted it. Let's hand out a little bit less. 25,000. As you can see, even though player 1 is the only one picking up drops, as long as there's some cash left at the end, it can still hand it out to compensate.